Okay, so let's see, 50K bytes didn't fit into the SRAM, I mean the SNVM. So I ended up having to back off to 32K bytes, and that passed. So now we're going to load it onto the, I'm going to click on Run Program Action, double click. Um, hmm. Oh, first of all, got to plug in the, let's see, that's what happens when I run Program Action. Run Program Action when it's not plugged in. Okay. Okay, that's in this error message. Um, oh, okay, so let's plug this in. Let's see. Let's device manager. Okay, ports. Nothing's there. Plug it in. There, plug the Flash Pro in. And now we get these four COM ports. Okay, so the board is currently powered down. Flash Pro is powered up. Let's see what happens. Then we'll click on Run Program Action. JTAG disconnect is shorted. Please check this. Oh, please check that the target board is powered. Nice. All right, so let's power up. Okay, the board is up and running. JTAG is connected. That's Run Program Action. While that's going, let's bring up soft console. Okay, launch. I already saw. Let's see. Cancel. Is soft console already open? I do. All right. So what we need to do is we need to sign or define a pointer for the address. So it looks like they did this for the UART in this address range. Um, I think I did it some too. Just trying to find it. So this is in the MSS UART. We want to work in the E51. That's where I'm currently working. That's one of the five RISC processors. So I'll go to this guy and let's go to the top. So I'm going and I'm defining. So I defined a variable of type UID32 pointer to it, and that I'm saying is an address 60 million. And how do you get that? So probably what for starting point is go to the MSS TRM, go down to the MSS memory map, scroll down through, and what we're looking for is FIC0, which is what we were editing. And, and you see FIC0 starts at 60 million, hex 60 million. So that is how you can find out where in memory things are, is with this memory map. Let's minimize him. So here we got 60 million. We got this guy here. It looks like the programming actually completed, so we should be able to do this. And so So in the previous test, I was writing to the LSRAM. I was writing 4,000 locations of 64-bit I guess 32-bit locations, because these are 32-bit values. And I was writing to 4,000 locations, and then I went and I read them back, and I had this at 4,000. Now let's see, what do I want? I've got 32K bytes divided by 4 is 8K words, 32-bit words. So 8192. So we're gonna rip through those. We're gonna, um, if any of them don't match the incrementing value, then we will flag a failure and we'll print it out. So down in here, when somebody, this is an endless while loop that came from the bare metal library. It's an endless loop that's receiving data from PuTTY, the UART. We're going to print out the fail count, which hopefully is 0. And then we're also going to print out the first 128 values just to see what's going on if it fails. So now we just click on the build. All right, finished. Now we're going to click on the run, left click. And this should run, and then it should suspend at the start of the program because we're in debug mode. And this resume light should be popping up. Do we have PuTTY? We do have PuTTY. So this is still from our previous session. This is from the one where I found PuTTY failure. Okay, so let's shut it down and bring it up just in case there's an issue. EUTTY PuTTY serial COM port 18 115 200. Open. Make it a little wider. To here. Start it running. Bring PuTTY back. All right, now we're at the point where you hit any letter, and that should tell us, and then our program will respond with the fail count and the first 128 values. Hmm. It looks like we loaded correctly, which is incrementing. Fail count is at 4096. So that's half of what we thought we'd need. To put in, we did put in 8K. Yeah, I'm pretty sure I did 30. Now let's just double check that so something's wrong. So 8K times 4 is 32K. What? 8K, 32K bytes. And let's see what we've got here. Let's go back to Libro. See what we messed up. Back to here. Back into here. Back into the LSRAM. Double click. These are all double clicks. LSRAM. The memory depth. Oh, so I'm saying the memory depth is 8192 by 64. So we still have the full memory there. But the let's see. No. Huh. Wait a minute. Wait a minute. Wait, 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 wait. Go back to here. Shut him down. Let's go to this FIC initiator. So we're going into this initiator, which is decoding the addresses. It's basically a bus splitter, sending some of the address space to the DMA, the rest of the address space to the memory. So we've got these configurations. And so we've got the 0 is the is 0 is going up to, let's take a look at it again. 0 here is connected to the DMA. 1 is connected to the memory. All right, and we go to the slave configuration. Oh, yeah. Okay, so I think they had an initial bug of where this was 0. And so I couldn't get past 4K. I boosted it up to 3 to get us to 16K. So that was the initial test. Now we have to boost it up to FFFFF, which is 64K locations. And that way we'll have the full address space and then we can get to it. So currently the reason we're failing on those last half, I believe, is because we didn't have the full address range. So click on OK. Let's do this again. Um, all right. Generate bit file. All right. I'll tune in a little while.